Graphing quadratics. Why do we want to graph these? Because we like to torture ourselves. But no, seriously, there's a lot of stuff that has the shape of a quadratic or of a parabola. But more importantly, as it relates to what we've been working on, you can solve these by graphing them as well. Meaning if we can look at the graph, we can actually find the solutions, which is what we've been doing with the quadratic formula. Completing a square and factoring and setting them equal to 0 and stuff like that. And what those really are is we're looking for the place where our shape here, called a parabola, actually crosses the x-axis, the horizontal line here. Wherever it crosses the x-axis, those are your solutions or your answers. That's what we've been focusing on for the past week or so. But they're also called roots or zeros or something like that. So solutions, roots, zeros, might be one other I'm thinking about. So wherever it crosses the x-axis, that's very important. Now, why do you get imaginary numbers and stuff like that if that's the case? Well, if I can ever get this to actually click on there. What if, looking at this thing right here, you see how it goes down forever and ever, or it should if it had arrows on there. It never crosses the x-axis. That's how you get imaginary numbers. Like the I that comes in, the negative number underneath the radical, happens when these shapes never cross the x-axis. And this one, if it was bumped up, it would never cross the x-axis because of the way it's shaped. And so that's how you get imaginary numbers. Now, there's other aspects of this that we need to talk about. One of which is called, this line right here, called the axis of symmetry. The axis of symmetry is reason why it's dotted is it's not a real line. It's basically like a place you can fold down the middle and it'd be symmetrical about that line or on that line there. And so that means it'll be equal on each side. Also, there's a point right here and right here called the vertex. The vertex is a point that, depending on where it is, if it's right here, it's at the, that's kind of big, it's at the bottom, and if it's right here, it's at the top. So what's important about that is to determine where it is, I'm cold, my hands are cold, my mouth is cold, so if I stumble like that, I'm blaming it on the cold. Now, if this thing opens up, our vertex is called a minimum. Why? Because it's the lowest point. Kind of makes sense to me. If it opens down like this, it's called a maximum. Why? Because it's the highest point. Yeah, it's down here. A lot of people get confused because, yeah, look, it's down below the x-axis. But I'm talking about as far as this shape, it's the highest point for this shape. As far as this shape, it's the lowest point for this shape. Okay? Now, how do you know if it's going to open up or open down? We'll talk about that in a second. So we got the axis of symmetry here. We have what this shape is called a parabola. Those are called roots, zeros, or solutions. And we can determine if it opens up or down. A lot of the stuff we could talk about is on this page, and you're probably going to have to pause this or whatever because I want to get right into it. Remember A, B, and C and stuff like that. But I really want to focus on down here. We can get into the nitty-gritty of how to actually find some of this stuff. Don't get intimidated by this. This is simply a point, x, comma, y. You get your x by using this formula, which is down here. Your y, how do we always find y? You substitute it in the equation for x to find y. That's how it always works. And so we'll go through this. I just want to show you as well. There's two other forms. We don't really use intercept form that much, but vertex form comes up from time to time. You can tell the vertex if it's written like this, and we got an example like that. So let's kind of go through this and see if we can make any sense out of